Today we're going to talk about combining PLTE with fiber, and really we're going to talk about quality of service and the needs of quality of service. So if we're going to use fiber where we have very high speed and lots of bandwidth, how do we back that up with private LTE? And in doing that, if let's say we have a fiber cut, we might not be able to carry all the traffic that there is, but we need to make sure the traffic that we do carry has good latency. Has to have the throughput, but a lot of the things we really care about in the grid, especially as we move forward to more state estimation, is more dependent upon lower latency or protection, being able to have these signals get through that help us reconfigure the grid in real time. And as more distributed resources come onto the grid, and the day when we reach more than, let's say, 50% of the grid driven by distributed energy resources, it becomes more difficult to keep the stability of the grid. Even anything over, let's say, 20% of the grid being powered by distributed energy resources makes it difficult. So all this new state estimation becomes very important. And also, you don't really want to drop like a traditional recloser or flizzer system that drops power on and off. How does the distributed energy come up and down off that? When you close back into it, you might close back into a system where all the distributed energy is gone, and it might take a while for it to reconfigure and come back. So not dropping those devices off the line becomes important. So I think going forward there'll be a push to do that. How many people have private networks or have networks right now in their utilities? How many utilities I have out here? And how many can tell me what the latency and jitter of your network is? So today I'm going to talk a little bit about it's good that you do, but most people I talk to can't tell me what the latency and jitter is or throughput that they have is. So I'm going to show you a little bit of the way that the commercial service providers do this and provide a technique that allows you to measure your systems in a very cost-effective way. So you don't have to go buy $20,000, $30,000 pieces of equipment. You can use some fairly low-cost equipment to measure that and have a way to characterize how the grid works, how your communications are working. So when some of the newer protocols that are coming are Goose messaging. How many people are using Goose messaging in the field area network today? So if you're using Goose messaging in the field area network, you got to know what your latency is. But also sampled values or PMUs, phase measurement units, to basically characterize the state of the grid and provide a real-time model of what's going on. So if you have a DERMS system in the future, or you're creating a DERMS system, you're able to dispatch VARs in the future in near real time to be able to correct whatever disturbances are going on the grid. So it's going to become more and more important to have these low latency systems. And then we're also going to have to support, the legacy SCADA systems, the DMP3 and things like that. So on the newer protocols, the Goose or IEC 61850 is one of the newer protocols that's out there. Eventually it will move into the field area network. There are a few cases where it has. Goose is the major area that's moved out into those networks. And it's used to control clusters of, let's say, reclosers or switches so you can reconfigure the network in real time. And how do you share that data with low latency to make that happen? The MMS is a way typically used in substations now, but it could be a replacement for what's done with a lot of DNP3. And sampled values is a way to bring real-time state data about the phase of what's going out on the grid. And as you get more distributed energy resources, you can get more reactive power and more disturbances down the feeders. And so how do you estimate that? And I think we have the Luma folks who, Tim Ouch, I think, is sitting here. They're starting to have problems with that, where they need to understand what's going on as they get more and more distributed energy resources in Puerto Rico. Because they have so many disturbances, there's a lot of people with diesel generators, with solar generators, wind generators. So how do they combat all this? And they need more data about the states in their system. And then we need to do the DMP3, which typically doesn't have much in the way of need for latency. A second is fine. One of the other things with these protocols is they don't tend to use very much bandwidth on let's say a per site basis. They might in aggregate use a lot, but when we're trying to have the LTE provide the connectivity there, like a typical Goose message will only use 10 kilobits per second, but it'll come in a burst. And when that burst happens, we need to get that data there right away. So we want to see ideally single digit millisecond latency, but even if we have 20, 30 millisecond latencies, we can make that work and get a lot of value out of those systems. And there's layer 2 Goose and there's layer 3 Goose. Most people today are using layer 2 Goose when they do it. Layer 3 Goose it's out there, but I have not seen it deployed in any production large-scale systems yet. Sample values and the C12, C37, 118. Typically, you can see longer latencies because everything is time tagged, but most systems want to see about 20, 30 milliseconds of latency so they can get that real-time estimate of what's going out on the line. So we need to think about more than just bandwidth. We need to think about what the latency of the system is. Now, we also, as we get more bandwidth out there, we start having fiber and this private LTE out there, we start bringing other things in like video. We could have work orders. We could be uploading, let's say, Linux boxes, their firmware, upgrading them, which is tens of megabyte files that are going out across the system. So we need to make sure that even though we have these broadband systems that are, these high bandwidth processes maybe going on, sharing the private LTE network, how do we make sure that the low latency stuff gets across it, and the low latency stuff is also characterized correctly in our boxes, or in our gateways at the edge. So things that are important, one is prioritization. How do we prioritize the data? And not all of the equipment that's out there is going to tag its data. So the routers and gateways need to be able to, let's say, tag that data based on what port it comes in. But many systems like the relays, the higher speed devices will have the ability to tag their data, which we can then map to different priority levels. Once we have the data mapped, we've got to manage the bandwidth. So we've got to make sure that we guarantee enough bandwidth for those critical applications while still allowing those other applications that aren't critical to have best effort at the bandwidth that's there. Maybe at longer latency, or if we just run out of bandwidth, we're going to what packets should we drop? Should we drop our video? Should we drop our file transfers? What things are the most important, and make a priori decisions about what is the most important thing to drop on the network. Because the only thing that grows faster than bandwidth is our appetite for bandwidth, right? We can always use everything that we have. So how do you make sure you use that excess bandwidth in a way that's valuable but not limiting to your critical operations? We want to leverage the jitter, and so if we don't have these quality of service mechanisms, what we can see is that things might get through, but they might get through with very latency, and there might be a lot of variability in how much delay there is. Sometimes it's really fast. Sometimes we have a lot of delay, and for control systems where we're trying to estimate state in a short amount of time, that latency can become a big problem and cause lack of stability and other things in the system. And then scalability, we need to make sure that what we have in the system not only accounts for what we need today, but what's going to come in the future as we continue to build more and more automation into the system, more and more devices. How do we make sure, even though we have enough today, we have mechanisms to make sure we have enough in the future? Any questions? So one of the things that will happen is we'll start to see virtualized private LAN services on these networks, where we have the ability to run different sets of data, logically isolated from one another, with the ability to have these low-speed low latency connections with enough bandwidth to meet the needs, a committed information rate for each one of those services, to make sure we can guarantee we're going to get the throughput and latency that we need. And probably one of the biggest use cases is the FLIZR, or the fault isolation and restoration systems. And today, most utilities I talk to say 5 minutes is good enough. We don't get hit on our metrics if we're within 5 minutes. But a number of utilities are starting to pay attention to the MAFI scores, the momentary scores, and they're beginning to use fiber to connect some of these circuits out in the field area network, the relays and things like that. So they want the ability, if fiber gets cut, they want the ability to use the private LTE as the backup for those systems. So we'll talk a little bit about that. There'll also be the PMU data, which is estimating state on the system. So that will be on its own land. There'll be the ability to do the DMP3 and that traffic to get through, but that's not very latency dependent, but it's also not very high bandwidth. The thing that'll make up a lot of the high bandwidth stuff is the stuff that's outside of this. Someone wants a video camera out there. That will be a best effort service, or a file transfer like I talked about before. So how do we make the most out of the use of our network? Well, we have to first of all classify our traffic. So like I said before, some products will classify the traffic and allow you to put tags on it. The legacy stuff isn't going to be classified. So you got to have a way inside your routers or gateways to tag that data as it enters the system from the edge. So you know this is important, or this can wait. You need a way to do scheduling. So once you have put these tags on this protocol data, how do you schedule that and have an a priori way of saying this is how we want this data to flow? We want packet prioritization. Which things should we prioritize? Even though we have allocated enough bandwidth, we need to make sure if we're getting tight and we're going to get latency, which ones do we want to make sure go first? So we want to make sure we keep that jitter low. And then resource allocation, we want to dynamically change how we do things if all of a sudden the bandwidth changes. So if you have a fiber cut, how do we know to switch over? And what we did 1 second ago, we're not going to do anymore because we don't have that much bandwidth anymore. So things might change quickly. We need the quality of service to be able to change quickly as the network changes. So what we're going to be showing today, what we're doing in the gateway, and then we're going to show you how we measure what we're doing in the gateway, is we have a queue of, right here I showed 3 different protocols, but we're actually just having 3 sets of data that we're going to put in at varying speeds, and we're going to run all 3 inputs at one time, and we're going to look at, as we bring the traffic over what the channel can handle, we're going to want to see that the lowest priority traffic is shed. The highest priority packet has no drop packets and no impact on latency. So we use the bandwidth that's available to get the traffic through. Once it gets through the system, we're doing the tagging here. This is coming out kind of ready to go into the LTE channel. We'll be using this data then to tag the QCI values and what traffic should get the higher priority through the LTE channel. So that we kind of pre-filter the data on what comes in, figure out what needs to be high priority in the private LTE channel, and then map that to the highest QCI value or the lowest QCI value to get the lowest latency. So how are we going to measure? Well, in the service provider market, they use something called Y1564, is a way that we can say what's the CIR we need, the committed information rate, what is the excess information rate? Well, you can have more bandwidth than that, but then when you get over that excess bandwidth and you don't have enough bandwidth, how do you drop data? How do we run a test like this? Well, we're gonna use low cost 1 gigabit per second NIDs that are used for by service providers. They have this functionality in them, and we're gonna run that through the gateway, through the RAD gateway, but you could run it through any gateway, and we can quantify what the throughput is, what the jitter is, what the latency is, min and max latency, and have a very nice test. And we'll run it through a series of steps to look at what happens as we increase the demands on the channel, and how does it gracefully degrade to provide bandwidth to the applications that need it. The metrics, the standard that provides the metrics is Y1731. So it provides a standardized way of looking at this jitter, latency, and throughput. So we're using a very objective way to do this. This is a way, how many people have used these methods in the past? So it's a good way. It's a little, in my opinion, it's a little bit of overkill because it was designed for networks that are going gigabits per second, but here we're going to scale it down and use it as a way to quantify the channel. And a lot of times I think what we're going to find when we do this is that the latency isn't quite what we thought it was, or the throughput wasn't quite what we thought it was. But what gets measured gets fixed. So once we can quantify it, we can begin to improve on it, and we can begin to look at what changes do we need to make to our networks to make them be as high performing as possible, and select equipment that is going to give us the ability to make the most of the bandwidth and functionality that we deploy. So this is our test setup. We have this running in our booth right now. You can come over and see how we run this test. And what we've done is we've connected the what we call the network interface device. We've connected it to the gateway through 3 channels that we're going to go from 20 megabits up to 20 megabits per second per Ethernet input into the box. We're going to use the quality of service to consolidate that into a single stream over a fiber connection, and we're going to run that through to to a NID on the opposite end. It's going to loop it back, send it back, and then it's going to measure the performance of that whole system. We are going to put an artificial constraint in the box so that we can constrain the channel down to watch what happens when packets stop getting through, and how the quality of service of the gateway restricts that. So we have our RAD view network management system is a graphical tool that allows you to kind of set it up and run it all automatically, but you can also run it through a CLI command set inside the box. So it's pretty portable. It fits all on one little table. It's very easy. It's very inexpensive. The NIDs are sub $1,000 devices that allow you to run this automated test and quantify the whole system. So what we want to look at is we're running it with fiber. What happens when we cut the fiber and we switch over to the LTE, and what performance do we get there? Now, before I'm going to kind of spoil the surprises. So far, what we've got to is verifying the test, verifying the performance of our SecFlow gateway and the latency through it. But we haven't, and we have the ability on our system to rapidly switch over once the fiber is cut. But we haven't had the ability to go into the labs yet and work and actually quantify the enteric system and the delay there. So that's going to be our next step, and I'm actually looking for utilities who want to work with us to do that. I found 1 or 2 already, but if you're interested in working with us to do this quantification and put together for your networks that you've created, we'd love to work with you to put these kind of measurements in place. So what are we doing? Well, what we do is we say, okay, let's set up the box, and we're going to set up 4 steps. So we're going to, in the beginning, we're going to say what's going to be our bandwidth per channel, what's going to be our bandwidth constraint, and what's going to be our packet size. And what we found is as you make packets big, you can get a lot more throughput through a system because there's less overhead to how you packetize and depacketize. As you bring packets down small, let's say to 128 byte packets, it cuts your throughput and it cuts the ability. You can put more transactions through, but you don't get as much throughput through. So we're doing this based on throughput, not packets per second. So you don't get as much bandwidth as you go smaller. Now, most of the grid stuff that we'll be working on, the PMU data, the Goose data, and even the DMP3 data is all small data. Everything's kind of 250 bytes or less in size. So you want to consider that when you do your testing to make sure you're not just using 1,500 byte PDUs, because you'll get really nice looking data, but it's not what you're actually going to see in the field. And we haven't done it yet, but it's probably smart to run on some of the channels, run the big packets, and on some of the channels, run the small packets. So maybe we should have taken the lower priority channel and run 1,500 byte MTUs, and on the actual control channels run 128 byte MTUs and see how the performance looks. Those are all things we can do as we evolve forward, but let's just show what we saw on this system. So what you end up seeing is here's 3 runs that we did. One we did with 1,500 byte MTUs, the packet sizes. We did 40 megabit per second channel, and we did up to 20 megabits per inputs. Remember, we have 3 inputs, so if all 3 inputs are going to 20 megabits per second, we'd have 60 megabits per second of throughput, which it all can't fit, right? So the quality of service has got to back it down. So if we look at the top one on throughput, what we see here is when we had 5 megabits per channel, which means we have 3 channels at 5 megabits per second, we'd have 15 megabits per second of throughput. We have enough bandwidth. Everything gets through. Our throughput's good on all 3 channels. Our packet loss is 0, and our packet latency is about half a millisecond. So everything's working fine. When we raise that now to about it would be 10 megabits per second. Now we're right at we're at 40 megabits per second. So we got 30 megabits per second of total throughput, 10 megabits on each channel. We're seeing no loss. We're seeing the latency stay very low, and we're seeing the packet delays low and the loss is 0. As soon as we go to 15 megabits per second, now our total bandwidth is 45 megabits per second. We're going to have some packet loss because we only have 40 megabits per second of throughput. So what we see is and this is step 3, we see that the lowest priority traffic, about 5 megabits packets, we're seeing the other channel is working just fine. We're having no loss, and we're seeing that the latency is going up on the channel that has lost packets. But that latency almost doesn't mean anything anymore because we have some packets with infinite loss, right? Because they don't make it through. But we are seeing that latency go up. But what's the good news is we're not seeing any latency on the other 2 channels where we had enough bandwidth. So the quality of service did its job and shed the traffic that it didn't need. When we go to, and we got about 40, we got our full 40 megabits per second of throughput. So our committed information rate here was 40 megabits per second, and it all just worked. When we're at the edge, it may be, you might say, we don't want to have over 2 megabits per second or 1 megabit per second coming from that edge spot, because you have to still share that bandwidth across your cell site, right? So you can use the gateway to give your committed information to come from that site, so you don't overflood your system from any one site but you still have all the latency and performance that you want. So we limit the rate, and then we map it into the QIR of the channel. So what we do prioritize should go, we give to the channel and say, put this across the private LTE in the lowest latency possible way. So just a couple other things. If you notice, the last one's probably the most interesting one to go through, is here we have 128 byte packets. We're going at a total of 5 megabits per second of throughput is where we've constrained the system to 10 megabits total throughput and 5 megabits per channel. Now these are still very high rates, but we're going across a fiber channel. So fiber has no problem having this much bandwidth, but we have a committed information rate that only allows up to 10 megabits per second here. So what happens is on the first two steps, there's no loss, there's no increase in latency, but as soon as we go to the third step, now we're above the committed information rate in the total throughput of the channel. So we see the low priority channels start to really fall off, and when we do the fourth step, even the second priority channel doesn't have enough bandwidth, it also starts to fall off, but the priority channel sees no impact in its performance, in its throughput, its latency, its jitter, stays just where you want it to. So using these techniques with the gateways, you can basically say we want to have a committed information rate from our field area devices. We only want so much bandwidth to go. Remember that the 61850, very low bandwidth. The DMP3, very low bandwidth. And the phaser data is also low. So probably with less than 250 kilobits per second, you can say we can handle all of our low latency stuff as long, or we can handle the bandwidth of our low latency stuff as long as we can keep the latency low enough so we can do the state estimation and the protection schemes that we need to do. So using quality of service allows us to do that. Using a method like we're using with the with the service activation test, to quantify it allows us to have the visibility and to make sure that our network is really performing the way it's supposed to perform. So when we do this, the next thing we'll be doing is we've tested here, we've tested to we're about to go into the LTE channel. The next step, as I said before, that we'll be testing is what happens when we put this into the LTE channel. That means we also have to add the IPsec encryption on top of that, which adds additional latency. But the biggest latency that we expect to see is the latency of the private LTE. We expect that to be somewhere between 10 milliseconds and 100 milliseconds at the priority, the highest level priority on the QCI. And has anyone here measured that? So I'm very interested to see what it is. There's a lot of theoretical data out there to see what we think it is, but what is it actually, and how does it perform as we put more data to the channel? What should we make the committed information rate that we give each site? And if we let's say we give each site a half a meg of committed information rate with a best effort of 5 megahertz or something like that, and we say, but we got to have a latency of 10 milliseconds. Can we achieve that? And if we can achieve that, then there's a whole bunch of new things we can do out on the grid for protection and state estimation. Even if we don't use it today, we know we have it. So we know our network performs to this level, so we can start planning projects, we can do advanced pilots, we can do other things to look at how the new protection schemes would work. And most of the equipment that you're buying, when you buy the, like the SEL stuff that Evergy is using over here, it has all these features in it. We just don't use them today. So getting your network to work with low latency will enable you to use these features that you've already purchased and are already in your equipment. Well, there's cues in there, right, that it's feeding out of. So it's making sure you're going to have some. If you don't have enough bandwidth, something's got to give. So those lower latency. If it's video, you're going to see your video break up. If it's a TCP session, you're going to just see it retry on the TCP, right? So probably TCP traffic will work fine. You won't even notice it. You're just going to have a little bit of loss. If 10% packet loss, you can probably ride right through it. If you're trying to do a voice conversation through that, it's probably not going to work. You're going to want to put yourself up a little higher in the QCI. But you can start to now architect how much data do we want to come at what latencies from the edge. And you can have control of that.
Yeah, that's kind of where it goes. You'll know based on your QoS settings what you're looking to spike.
Yeah, and the test that we did here, when we go to this when we go to the step 4, we've basically abused the system. We've said we're going to put 150% of the throughput that we can get through into the system, and we're going to say, what does the quality of service do when we do that? And what we want to see is that the really important stuff doesn't get affected at all, which it doesn't. So this here is what's happening in the gateway that we're showing. This process then is used, as I show in the next slide. This is used once we get that data, so we say, okay, here's the important data. Now we need to map the important data into the QCI that's in the LTE channel, so that the important stuff gets across the LTE channel with as low a latency as possible. But it's fighting with quality of service issues from other sites, from other users. It's not in control of those. So the quality of service we have here is when we have data coming from a single site, let's make sure we prioritize what we want to send to the site and then use that to make sure we put the right stuff in the LTE channel. So this is all, RAD does this a lot with all of our commercial service providers. So this is our big market, and our engineers have, we have a lot of engineers, they develop this in ASICs as well as in, also as we start to understand how you want to use the systems, we could customize this if we find, as we measure, there's some interesting new use cases, we can customize this to however is best going to fit your use cases. So kind of in closing, we have this. We talked about all these really high bandwidths, but we're looking at again when we look at quality of service for like with the Linux system itself that we're using, and we're doing a 2 gigahertz dual core product in our gateway. We're really seeing less than half a millisecond of latency through the system, which is very good from a grid standpoint. We always compare everything to a cycle, and 5 milliseconds is considered real time. So the gateway itself has not used up much of this budget that we have for latency. The next comes the IPsec delay. That should be a 0.5, and there's a decimal point missing there. But from about a half a millisecond to 100 milliseconds, this is depending on how people implement it, what kind of accelerators they use in the products. We have a very good IPsec accelerator in our product. We're very low latency, but not all products will be. The Enterix delay, it could be as low as 10 milliseconds. I'm thinking it's going to be between 15 and 50 milliseconds at the highest priority QCI level, but that still is yet to be measured, and I haven't found anyone who, including the Enterix guys, who can tell me what it is. So I'm really looking forward to using this method to quantify that. And then LTE delays without QoS, without using the QCI or the QoS that's here, I think you're going to find you're in the 80 milliseconds to 300 millisecond range, which is still very good. It's going to be very much like if you use LTE. If you're doing roaming, so there's some of these cases where when you fall off the LTE network and you roam, your latency is going to be much longer because now there's a whole extra step of things that you need to do. So if you're roaming, don't count on your count on it being a half a second. So I think we can test that when we run this also. What is roaming latencies? What are when you're directly on the Enterix network, what's the latency going to be? So to me, this is really interesting because I come from, my background was I was at MDS. I was the vice president of engineering at MDS. Now GE Lenovo or GE. What? Vernova. Yeah, Vernova. And so I come from a place where we did a lot with polling and lower speeds. And so this private LTE opens up a whole new world of being able to do this state estimation, drive the grid to the next level, and really improve performance. So this is really what it's about. When we get latency down, we can do all kinds of cool real-time control things. So quality of service is just super important. And being able to use fiber, so once we get all that fiber out there, now most of the sites won't be taxing the private LTE network. But when we need to use that private LTE, when we have a fiber break, we know we have the performance of those nodes with quality of service to fill the gaps until we get that fiber fixed. So I think that's where it will go in the future on the really critical things, and I think the secondary sites will also have low latency that don't have the fiber. So now we know we can get the performance that we need using the quality of service that's available. Questions? I can, if you look, like here's an example of the data, and the jitter here, they give min-max, the jitter was in there, but we didn't record it in the thing, but there is a jitter spec. Right now it's min-max, so like in this case here, the min was 0.627 milliseconds, the mean was 0.7, and the max was 0.95. So you can kind of get an idea of what your jitter is by just doing the subtraction there. Is it what? Yes. So you can see it here. Go back on step. So this is step 1 here. So it was from 0.6 to 0.9, and on the last case, actually, it went when we fully loaded it up. It went step 4. It was 0.66 to 2.5 milliseconds. Compared with if you looked at the other ones, we've kind of overloaded it by 50%, the channel. So it did get a little higher, but it still kept the latency very low. If we go to the next slide here, you can see this is this use case here. We can see the latency stayed very low in that use case. So it's pretty much flat compared to all the other channels went up. You probably wouldn't want to have pushed that to more than the step 3. So if you just kept it to step 3, you wouldn't have seen any change in the jitter at all, and you were already losing a lot of your your second level priority traffic. So you were a little oversubscribed, but quality of service was working well. When you really push it, that's when you may have an issue. And we were also pushing it on 4 channels. So every channel was having to prioritize a lot of the queue. So right now our failover times are in the, well, we use a ping to do it, so it depends, but we can fail over in a quarter of a second or half a second pretty easily. If you use we have the fiber systems there, so we can fail over even faster if we run like a Y dot, I forget the standard, but there's a standard where you can fail over in less than 100 milliseconds without too much problems. What it will do when it sees the fiber come back, it'll just automatically switch back over. We have a paper, it's called our Duo. There's a paper in our booth about how we do the failover in the box. Yes, Aaron. It would support jumbo frames. We can look at that and look at what the performance impacts on the network are. My assumption is the performance is going to be limited by the LTE channel. So do you want to send jumbo frames over fiber? But just remember that the use case here is from a single site. So what happens is the PMUs are aggregated, right, into bigger sets. And that might be where they're using the jumbo frames. So that would be like you're sending to a substation or a PMU aggregator, and the aggregator is making these big frames. Because the actual PMU data is pretty small. You can go from 1 to, I think, 60 samples per cycle, and it doesn't fill up a 1,500 byte packet. It does? Well, it will be a good use case to test. So we'll use this method and we'll come up with what are the benchmarks that we see, because everything is pretty stable. It's just figuring out how well things perform and how to optimize what we have. What gets measured gets fixed, you know? So if it doesn't work well, we'll figure out the best way to use it. Any other questions? So do you guys find this interesting though? I mean, I think it's good. I think it's when you start asking what is latency, it's not something we've typically asked in the industry. We've always talked about it, but we haven't really expected it to be as low as we think we can get it now. So we need to make these measurements and come up with what is the real performance we're going to see on these networks. And that's going to lead to a whole bunch of new use cases. I think the Goose messaging requires the
I guess Goose is a protocol that's supporting the use case, right? So what?
fault restoration, you know, trying to do it in a hitless way where your customers that aren't on the faulted line don't see any power loss, and you don't kick all your DERs off, and have that whole struggle of, especially if you have a high density of them. It's going to be a lot harder to get everybody back on in a reasonable period of time. Also, you can get, you know, lines can get a lot more reactive. That's really not the default, but getting a good estimate of state, the lower the latency you have, I think the better you can estimate the state of those lines. I think the gentleman before us was talking about state estimation too. So, I mean, everybody's trying to build these models and understand what's going out as we create more energy on the feeder as opposed to pumping it into the feeder. I think there's a lot of use cases, and I think there's a lot of equipment out there that if you get lower latency, they can do more with the equipment you have. All right. Thank you.